Okay, so welcome to lecture 36, which is the very last lecture of this semester, where we will talk about entropy. So we will define what entropy is in a bit, and it's still related to what we've been talking about. We've been talking about the laws of thermodynamics. We started by talking about the first law of thermodynamics, which is conservation of energy. The change in total energy of a system is equal to whatever energy is input plus or minus whatever energy is taken out because of work. And then we learn about the second law of thermodynamics. And the second law of thermodynamics is quite a broad law. The general idea behind the second law of thermodynamics is that it's a law that tells us what can happen naturally, what is possible in nature and what is not possible in nature. That's the broad idea of second law of thermodynamics, but it can be stated in specific statements. And in the last two lectures, we have looked at some specific statements. Firstly, we learned that heat will flow spontaneously from a hot object to a cold object. This is a statement of the second law of thermodynamics called the Clausius statement. And based on the spontaneous heat flow from hot to cold, we learned how the heat engine operates, because as heat flows spontaneously from hot to cold, it does work. And the work done is the output of the heat engine. And by looking at the efficiency of the engine, comparing the output work to the input heat, we learned that the heat engine cannot be 100% efficient, and that no engine can completely transform heat or thermal energy into mechanical energy or work. And we learned how there is always heat waste in any device, and that is the Kevin Planck statement of the second law of thermodynamics. And then we went back and said that, okay, if heat will flow spontaneously from hot to cold, then it's also true that heat will not flow spontaneously from cold to hot. Right? And in order for heat to flow from cold to hot, work needs to be done to facilitate the heat flow from cold to hot, because it will not happen spontaneously. And by putting in some work, we can make a hot room hotter or a cold fridge colder, and that's how we then related the second law of thermodynamics to the operation of refrigerators and air conditioners and heat pump. That was our lecture yesterday. Okay, so as we can see here, there are many statements, and any other statement you can come up with. Say, for example, when you put ice in hot coffee, the ice will melt and the coffee will cool down. This is also a valid statement of the second law of thermodynamics, because it's a direct consequence of Clausius statement, the first Clausius statement. And so we need a general statement for the second law of thermodynamics that will cover all of the situations needed. Because as you can imagine, these three statements, they're specific to certain situations. The first statement is specific to the heat engine. The third statement is specific to the refrigerator, air conditioner, or heat pump. So a general statement of the second law of thermodynamics can be stated this way. It says that the total entropy S stands for entropy of any system plus its environment, increases as a result of any natural. When we say natural, we're referring to irreversible or real processes. So just a reminder, when we say irreversible, we are talking about natural processes or processes that happen in reality where there is friction. Okay? And all processes in reality are reversible because there's always friction present. And the second law of thermodynamics says that in any real process or in any real event, the total entropy of the system plus its environment increases. Okay. In mathematical form, we can write that here as the change in an entropy of the system plus the change in entropy of the environment is greater than 0. And we'll talk more about this equation later on. But you're probably wondering, what is entropy? It's a new term that we've encountered this semester. And maybe we'll have a better idea of what entropy is if I rewrite the general statement of second law of thermodynamics in this form. The natural or irreversible or real processes tend to move towards a state of greater disorder. Right, so instead of using the word entropy here, I used the term disorder. And second law of thermodynamics tells you that maybe in the beginning of the week, you start with a clean and tidy room. And no matter what you do, at the end of the week, you end up with a messy room. All natural processes tend to move towards a state of greater disorder. And so entropy, we can define entropy as the measure of the amount of disorder in a system. It tells you how orderly or disorderly a system is. Here's an illustration. You have here this ball. It's highly ordered. As you can see, each pieces are arranged in such a way that it's compact, and you can see the order for which the pieces are arranged. And then this is a more disordered system with the pieces scattered all around. Okay. So in terms of entropy, we can say that the highly ordered system has low entropy, S entropy. We use S to refer to entropy. So this highly ordered system has low entropy, and the more disordered system has high entropy. Right. Okay, so usually in any natural process, you start with a highly ordered system with low entropy, okay, clean, tidy room, and you end up with a more disordered system with a high entropy, messy room at the end of the week. Anyone who's been to my office at the beginning of the semester and then at the end of the semester would have observed exactly this second law of thermodynamics at play. My office is always clean and tidy at the start of the semester, and at the end it's just a mess of papers and demonstration materials everywhere. All right. And so second law of thermodynamics tells us that, you know, it's a natural process. You'll always end up with a highly disordered system. And so we can also say that the entropy and second law of thermodynamics, well, entropy specifically defines which event happens first, because it's very specific. You start with a nice orderly system, and then you end up with a disorderly, messy system. So we sort of, the entropy sort of gives us an idea which event happened first. Okay? You start with an orderly system, and which events happened last, whichever or disorderly system happens later compared to the orderly system. And this happens everywhere, and it happens everywhere without us knowing that it eventually build up this intuition of entropy, and entropy being the times arrow, meaning the entropy pointing to which event happens first and which event happens second. So for example, if I show you this video clip, all right. And if you see such video clip in a movie, right, how do you know that the movie is backwards? We probably all have the intuition that if you see some clip like this, you know that it's being played backwards. isn't it? We sort of have this natural intuition to know that this clip is being played backwards. And how do you know that this movie is backwards? Because we know that it's to see what happens here. It's the broken glass being assembled into a pristine glass, right? That's what's happening in this movie clip. But we know that it's highly unlikely for a broken glass to spontaneously repair itself into a pristine glass, right? The broken glass is, of course, the disorderly system, and the pristine glass is the orderly system. Okay. And so the second law of thermodynamics and entropy tells us that events and processes usually start with an orderly system of pristine glass, for example, and eventually if the glass falls, it will break and you end up with a broken glass, a disorderly system. So entropy being the times arrow tells us that the pristine glass is the first event and the broken glass is the second event. Right. So we always go into increasing randomness, okay? Just like you start with an orderly, clean, tidy room, you end up with a messy room, and it's highly unlikely for your messy room to tidy up itself and go back to an orderly state spontaneously, right, by itself, without your help, without input of work from you. All right, so is the concept of entropy quite clear? It measures the randomness and orderliness of things, and it tells you, and together with second law of thermodynamics, it tells you that processes start with being orderly and end up being disorderly. All right. So in second law of thermodynamics, we actually want to determine whether entropy increased, whether the system became more orderly after some time. And so it's more useful to determine the change in entropy rather than the absolute entropy, because we are comparing two events, two states. Okay? You're comparing the pristine glass and the broken glass, or your tidy room and your messy room. So each of those events, each of those states, of course, will have their own entropies. But what is more important is the change in entropy, how the entropy changed over time. Okay, and we don't care about how we've gone from orderly to disorderly. In other words, the change in entropy is path independent. We only care about the initial and final states. We only care about in the beginning of the week, your room is clean and tidy. At the end of the week, it's messy. Okay? That's all we care about. We don't care about whether in the middle of the week you had a party and that's why you ended up with a messy room, or you just become busy and that you didn't, have time to tidy up in between days. So we don't care how you went from one state to another state. Change in entropy is path independent. We just care about, okay, this is the initial state, this is the final state. How did the entropy change? How did the orderliness of the system change? Okay. And so if we wanted to find the total entropy, so I should say here, I should add here total change in entropy, then you are also looking at the change in entropy of the system plus the change in entropy of the environment. Again, as a reminder, when we say system, it's the object that we are observing, and the environment is everything around it. So say, for example, with the ice being put in a hot coffee, if you want to observe the melting of the ice, so your system is the ice, the ice, which is the system, loses energy, and the environment, which is the coffee, is where the energy lost from the system goes to. Right? Okay. And it says here that the total change in entropy should consist the change in entropy of the system, the ice, plus the change in entropy of the environment, of the coffee surrounding the ice. If the process is reversible, and this is reversible meaning perfect or ideal, then the total change in entropy is 0. Okay, but in reality, all processes are irreversible, so natural processes are irreversible, so the total change in entropy should always be greater than 0, meaning change in entropy is how much disorderly an orderly system has become, and total change in entropy being greater than 0 means that you always end up with a disorderly system. Right, are we still okay up to this point? So we've defined what entropy is and related it to the second law of thermodynamics. So now that we understand what entropy is, we should know how to calculate entropy. So how do we numerically determine the entropy? The entropy depends on temperature. Right? So if you think about it, if you think about an object gaining energy, the temperature of this object increases and the molecules start to move randomly. And as they move faster and faster, the system becomes more disorderly. So it just makes sense that the change in entropy will depend on the amount of heat that is put into a system, because if you heat up a system, right, imagine a water that you boil. As you heat up the water and starts to boil, it forms these bubbles and it starts to become disorderly. But the amount of heat you put in will also affect the temperature of the object. So the change in entropy depends both on the heat and the temperature. Okay, and it's not such a simple relationship, because it's the integral of the change in heat or energy with respect to temperature. But in this course, we'll only cover the simplest cases for when the temperature is constant or when the temperature change is small. So this is, so this is the general equation. This is the general equation for the change of entropy. But in our course, we will only go up to the level where the temperature is constant, in which case we can take out temperature out of the integral and we just get the integral of dq that's equal to q. So the change in entropy will be equal to heat, either heat that's added to the system or taken away from the system, divided by the temperature. Right, so this is the first case that we will consider. The second case is when there is only a small change in temperature, in which case we get the average temperature and use that as the temperature of the system. Okay, it's really important that temperatures are in Kelvin. So make sure to convert Celsius to Kelvin when you're calculating for the change in entropy. It's related to temperature, but temperatures have to be in Kelvin. Okay, we're now left to look at some examples to tie together the concept of entropy to real situations and how we use these equations to determine the change in entropy. So you have here steam, 250 grams of steam It's at 100 degrees Celsius. That's the boiling point of water. So steam can also condense to water also at 100 degrees Celsius. When steam condenses to water, it changes phase. And we want to determine the change in entropy. Different phases have different degrees of orderliness, and that's why it makes sense to determine the change in entropy, right? Gases, they're free to move, so they have more they are more disorderly compared to liquids or solids whose atoms are just more arranged in a more predictable pattern. So here you have steam, gas phase, condensing to water. What is the change in entropy? And does it violate the second law of thermodynamics? All right, change in entropy is the heat either added or taken away from the system divided by the temperature of the system. All right, so we are turning steam to water, changing phase from gas to liquids. And we learned that if you undergo phase change, then the amount of heat is equal to the mass times the latent heat. In this case, you're condensing, so it's the latent heat of vaporization. Right, it's negative because the steam loses energy. The steam needs to give off some of its energy to the environment in order for it to condense to liquid water, right? And so that's why it's negative. But you have there the mass, convert that to kilograms times the latent heat of vaporization, joules per kilograms, right? So that's why you had to convert your mass to kilograms. And you have there the amount of heat that's released by steam when by the 250 grams of steam when it condenses to water. Okay. And as a result of this energy released by the steam, the entropy, sorry, there should be a negative sign here, the entropy of the steam will change. Okay, and the change in entropy is equal to the amount of heat that's released, negative 565,000 joules, divided by the temperature of the steam. Again, take note, temperatures need to be in Kelvin, and hence you have to add 273 to the Celsius temperature. So you have a negative change in entropy. Right, it is possible to have a negative change in entropy. As we've seen here, it's the case where the system loses energy. Okay, this is the change in entropy of the steam. The steam is the system in this case, and it's negative, as I said, because it lost energy. But overall, the total change in entropy should be greater than 0. Okay, you get a negative change in entropy. It doesn't mean that second law of thermodynamics is violated because it's not greater than 0. It's not positive. Second law of thermodynamics says that the change in entropy of the system, the steam, plus the change in entropy of the environment is, you know, the where the energy of the steam went to. Okay. It should be a combination of these changes of entropys. And to satisfy the second law of thermodynamics, if the change in entropy of the system is negative, it's negative, right? Then the change in entropy of the environment should be positive. So that if you're adding a negative number and a positive number, you will get a positive total change in entropy if this positive number is greater than the negative number. In other words, the change in entropy of the environment should be greater than the change in entropy of the system. So two things that needs to be satisfied. The change in entropy of the environment should be positive, greater than 0, and it should be greater than the change in entropy of the steam. Right. Any question with the maths? Practically, what does this mean? Right, you have the steam condensing to water, gas phase, so gas molecules, they're more disorderly, they're free to move about freely. When they condense, they become more orderly, like gas becoming liquid. Liquid is a little bit more orderly than gas, and hence you have this negative change in entropy. But then the total change in entropy should be positive, meaning the energy released by the steam that went into the atmosphere caused the gas molecules in the atmosphere to move faster, right? So the entropy of the environment, the atmosphere where steam released its energy to, the environment became more disorderly as the gas molecules around absorbed the energy from the steam, and hence the gas molecules around moved faster than they originally were. Right. So that's what these negative numbers and positive numbers mean. Right. Okay, let's look at another example. You have here 4,000 joules of heat. So you are given Q right away. 4,000 joules of heat is occurs between two rooms. So you have a hot room at an average temperature of 37 degrees Celsius, and you have a cold room that's at an average temperature of 27 degrees Celsius. Okay. Right, so two rooms at different temperatures. We learned that if two objects are at different temperatures, heat will transfer spontaneously from hot to cold. So heat will move out of the hot room and move into the cold room. It's given here that 4,000 joules of heat will transfer between the from the hot room to the cold room. We want to find the total change in entropy. So you can consider the hot room to be the system, right? And the cold room to be the environment, because heat will go from your system to the environment. So still the change in entropy is heat divided by temperature. And you sort of have two objects here, the system and the environment. System, you can consider this, as I said, as the hot room, and the environment as the cold room. So you have to get the change in entropy of each of the objects, right? Change in entropy of the system and change in entropy of the environment. So for the hot room, the change in entropy is the amount of heat that's lost divided by the temperature of the hot room. And again, this negative here means heat is lost. Right, and the problem tells you that 4,000 joules of heat is lost. Right, carry over that negative. Temperature again needs to be in Kelvin. and you end up with a negative 12.9 joules per Kelvin. Okay, again, you have negative because heat is lost from the hot room. For the cold room, it's the amount of heat that goes into the cold room divided by the temperature of the cold room. In this case, the heat should be positive because the cold room gains heat, gains energy. Right, so it's just positive 4,000. And the problem tells you 4,000 joules transfers from the hot room to the cold room. Again, the temperature needs to be in Kelvin. Right, so the change in entropy of the, sorry, for the cold, this is cold room. The change in entropy in the cold room is expected to be positive because it gains energy, it gains heat, its temperature increases, and therefore it becomes more disorderly. But overall, the total entropy, the total change in entropy is the sum of the change in entropy of the system and the environment. Hence, you add up the change in entropies of the hot room and the cold room, and you should end up with a positive number. So according to the second law of thermodynamics, the total change in entropy should be greater than 0 for real or natural irreversible processes. So overall, the total entropy of both rooms increased. You can think of it as the air molecules in both rooms becoming more disorderly. Okay. All right, any question about the two examples? So these two examples showed the total change of entropy for irreversible, natural, or real processes, where the total change in entropy should be greater than 0 or positive, as we see here. And just for completeness, let's look at an example of a reversible process where the total change in entropy is equal to 0. Reversible processes, again, they are ideal, they're perfect, but they don't really occur in nature. We assume that there is no friction in this case. And one example is the isothermal process. So the processes we looked at, isothermal, isobaric, and isovolumetric, because we used ideal gases, they are usually reversible processes. So, but here we'll just look at the isothermal process because it's when temperature is constant. An ideal gas undergoes isothermal expansion. Okay, when it expands, its volume doubles. Okay, we want to determine the change in entropy of the gas. And we again start with the definition of a mathematical definition for change in entropy. It's the heat divided by temperature. So a little bit of memory recall is required here. Okay, when we have an isothermal process, the first law of thermodynamics you have, it says that the change in internal energy is equal to heat minus the work done, right? And the change in internal energy depends on the change in temperature, 3/2 nRT. In an isothermal process, temperature is constant, right? In an isothermal process is iso, meaning the same thermal temperature. In other words, change in temperature is 0, hence internal energy is 0, and we learned therefore that the heat is equal to the work done. Whatever heat you put into an isothermal process goes into work done in expanding the gas. So everything we learned so far all ties in with this last lecture here. Okay, so therefore, if we wanted to find the change in entropy, we need to find how much work is done in expanding the gas, okay? Because the work done is equal to the heat. The amount of heat added to the gas goes into the work done in expanding the gas. Okay, in an isothermal process, how do we find the work done? Yes, it's the one with Ln, where you had this integral of dV over V, and you ended up with nRT Ln Vf over Vi. Right? Yes. Okay, so this is the work done in an isothermal process. We plugged it in. All right, so this one here, we substitute into the expression for work. Right, I just substituted the expression for work into the change of entropy. So change of entropy will be nRT Ln Vf over Vi divided by T. So T cancels each other out in the numerator and denominator. Okay, we can simplify this further because the problem says that the volume of the gas doubles. That means that the final volume is twice the initial volume. In other words, Vf is equal to 2Vi, 2 times Vi. And so you can cancel Vi in the numerator and denominator inside the Ln bracket there, and you end up with change in entropy equals Nr times Ln2. Okay. All right, so this is the change in entropy of the system. Meaning the expanding gas. That's our system. Right, and there's a follow-up here. What is the change in entropy of the environment? Assuming this is a reversible process. Right? The environment is where the energy came from to expand the gas. Right? It could be a stove that's heating up some gas in a container. That could be the environment. So it can be anything around the gas that gave off some energy that the gas absorbed. Okay, if it's a reversible process, an ideal process, then the total change in entropy should be 0. Total change in entropy should be 0, so that the change in entropy of the environment is this negative, the change in entropy of the system. And that's why, you know, reversible processes like this do not exist in nature, because this tells you that the change in entropy is just negative of each other, meaning they're of the same orderliness. Okay? But in reality, second law of thermodynamics says that everything should become disordered. Okay. So this is just an ideal case, ideal example, just to illustrate how we use this total entropy equals total change in entropy equals change in entropy of the system plus change of entropy in the environment being equal to 0 for reversible processes. Yeah. So we will, ideally, we will either let you know it's a reversible process, or if it's one of those, you know, isothermal, isobaric, isovolumetric processes, you can assume that those are reversible processes. Otherwise, you know, like an ice melting in hot coffee, this is an irreversible process. Or hot air transferring from a hot room to a cold room, like the previous example, those are real processes, irreversible processes. So total change in entropy should be greater than 0. Any question about entropy and change in entropy, or the examples we looked at? Right, so if there are no questions, this ends our lecture in entropy, and also ends our semester lectures, the topics that we'll cover for the semester.